Hi everyone, I'm Sanya, and today I kind of want to talk about an example of how you can go from estimating a probability weighted matrix to getting, an information content logo. Where you're trying to predict what are the heights basically of each of the bases that you would expect along certain positions in a motif. So let's get started. And again, please let me know if you have any questions at all. And we kind of discussed in some other videos about, expectation maximization and Gibbs sampling approach for how we can kind of determine the motifs. Where transcription factors could bind along, a set of DNA given a set of sequences and other information as well. So now we're going to kind of work with that probability weighted matrix where you have information on, the background, the non-motif bases, the probabilities that it's an A, a C, a G, or a T, like for DNA. And for RNA that, T would be replaced with a U for uracil. But how you can go from non-motif, as well, which is the background, but also positions along the motif. So in this example, we're going to have a motif that has 11 bases. So it's kind of a big chunky motif. It's pretty long. And we're going to try to say, how do we find the heights of each of those bases? And you're going to see that a lot of that comes down to how certain we are in a particular spot in the motif that we have a certain DNA base. So we're going to get started with this example. So in this example, please suppose that you have estimated the motif model by running mean, it's expectation maximization algorithm for motif discovery, but whatever it is, you have estimated a probability weighted matrix. So in this example, you have these 4 DNA bases, A, C, G, T. This is the, non-motif, the background position, K equals 0. These are all, percentages. So what you do know is that, these will all add up to, that these should add up to being 1. So this would be 2, 1. If you add these up, you should also get 1. 1. All of these sum up to 1. So you pretty much, you have these different positions along the motif. And what you want to do is you want to convert this probability weighted matrix to an information content logo. So how do we make that happen for us? So here is an example again of another probability weighted matrix. So, like here, just not having the background here, but we do have a, in general. But what we would do is, what we want to find is we want to come up with an information content logo for the different positions along a motif. And let's say that our motif here in this example is 8 bases. So what we would do then is we are going to say, okay, well, motif with 8, DNA bases. So we have a DNA that can be 8 bases long. And what we are trying to do is these are the probability weighted matrices, matrix that we have. And what this is saying that the first position of the motif, what we predict is about 50% of the time we will have a C in the first spot in the motif. So what you would tend to see is that maybe there should be a lot of the C here. It, usually takes place, 5 times out of 10 or 50 times out of 100, that we expect to see. Then we're kind of tied with G and T, so 20%, 20% of the time. So it's about almost half this height in a way of the C in terms of the frequency. And then there's this A over here. And then this A is pretty much telling us that it's about half the height of this. So if you think of this, and why is that the case? It's because, so if this is 5, then if you take this in half from here to here, this would be roughly, this is roughly like half of this. And that's where we kind of map the heights. So we really are expecting to have a C in the first spot, then a G or a T, a tied, then an A. But now if we look in the next spot in position 2 of our motif, so these are all positions along the motif, we expect like to have A's and T's a little bit more. So those are, heavier here. Those are like taller. Then C's and G's are kind of tied. So you notice that the priority is usually given to the one on the top that's that's the likeliest to happen. But if they're ties, then we maybe just alphabetize them, and they look virtually the same. But where would you expect most certainty to happen if you were to look here? Like which position maybe? So if you want to pause it to take a guess, where would you expect it to be? So just pause it and think, okay, well, where do we expect most information to be found? And what you will find is that if we look here, we find that 70% here, this is a huge number here. So this means that 70% of the time, if we're looking at the last spot in the motif, we would expect it to be a C. So this maps to this being really high. That means we really know that most of the time we would expect a C, an overwhelming amount of the time. Here as well, in this fifth spot, which is here. So these are all, you see 1, 2, 3, 4, 5, 6, 7, 8. These all kind of map to these. So just to make that a little bit clearer, what you'll find is that each of these maps, to here, which is a frequency logo. And also here, but this is, kind of an add-on from the frequency logo. This is an information content. So you'll see that they're both analogous. They're both kind of the same, but it's just like the information might differ. And what we're trying to get is, this is our goal here, is to get the information content logo. But I'm trying to say that you can go from a probability weighted matrix to either interpretation. So this is a probability weighted matrix. That's what this is. This is a probability weighted matrix. And we want to go from here to here. So we want to basically have this pathway that is here. We want to have that pathway. But I'm trying to say that you can go from either or in a way. But when you see that you have a lot here, this is like a high number, that means you really know that this is a C, most of the time. So that's like a lot of knowledge. Like imagine if you were kind of on the fence between the two. Like you didn't know, like over here, it's like, it could be the only information that we get in this spot. So that's where you see like virtually you don't have any extra information. It's like if you are, playing cards, or you're playing something, or you're gambling or something. I just don't do that. That's not really good. But if you're doing something, or like, picking a stock, for instance, if you have some insight, okay, I think this company is going to do well or something, then you have more information, or if I tell you, okay, I think it's equal, or, either or. It could be raining tomorrow. It could be, so if you live in a really cold and dreary place, you're probably going to have more, you're going to probably have more information that it's going to be cold and dreary the next day versus if you're living in sunny Florida, for instance, or California. So that's sort of, hopefully, or if you're living in, I know in London, it's supposed to be rainy a lot, but whenever I've been there, touch wood, weather usually cooperated for the most time in London. But in any case, the information content is sort of saying, how much additional information do you know? So if these are really close to 0.25, which is what they would be if there's equal chance of all four of them, then you don't really expect to have much information content here. So you see that this is virtually not, virtually non-existent, and that 7 is virtually non-existent. Similar kind of idea going on over here, but you don't really have much information. But as you know that if you narrow down to maybe 1 or 2 bases that are really likely, your information content will spike up. Like this is much higher. It's really going to be a C, and it's a lot higher than, like this is a lot higher than this. This is a little bit lower, because you have less information at this position. Even though it's 60%, it's still not as good as knowing 70% of the time you expect a base. It's almost like, you don't give it much information. If you're an only child, if your parents or guardians say, oh, you're my favorite child, you're like the only child. It's not much information you got from that, right? So that's what I want you guys to think, is that the more we know that it's different from 0.25, 0.25, 0.25, 0.25, the more information we have. And if we know it's really highly likely to be a base, then we are, even better off. So like here at the 6th base, we kind of know that, okay, well, it's 40%, it's an A. That is still something. 10%, this one, it's kind of, it's the same, similar. So the idea is that, we see C here, the more likely it is to be a certain base, the higher this will be. It just so happens that this is the last base as well, but When you think in a 5' to 3' direction for the DNA as well, as we're going across, what we observe is that there's more likelihood to be a C, so that's why it's higher. So the height is sort of telling us, do we have more information? Is this a valuable piece of information that we've gotten? Because again, guys, the benchmark, what we typically expect is, that we would typically expect each of these to just be 50, like all equal, so 1/4 for all of these each. So if we do really different, like, so here, we think it's going to be probably a C in the spot of the motif. Here, oh, I can't really say. I know it's going to be like an A or a T, but it's just marginally different. Here, maybe we can also say, okay, this, and okay, this is good. Yeah, this is okay. This is also pretty good too. So you can see that this is a likelihood to be a G. So this would have like, pretty much similar height, for both of these. Oh, sorry, I'm not really good at sketching. But anyways, that's sort of what you would expect. But anyway, so what we really are trying to do is we're trying to just go from here to here, like from a probability weighted matrix to an information content logo, where, you have the height in bits, and I'm going to kind of explain how we go about that. So what we have in the frequency logo again is the height of each character. C is proportional to the probability of C. So this height is proportional to this. So if you think of what this y-axis is measuring here, then this y-axis is just measuring the probability of a given base. So what you will see if a given base, a probability of, maybe I should write it like probability of a given base. So what you're going to observe is the same height. This is, if you think of, oh, okay, I can't sketch. Okay, okay, so if you think of this all just being the same, it's all one. And what piece of the pie do you get? So here, this gets a huge amount. So the height is proportional, same height. That is what this frequency logo is telling you. That's what this is telling you here is, the height is proportional to the probability of that base, the probability. Whereas for an information content logo, what you're going to observe is that it's based on the entropy of a random variable C representing distribution of character states in each position. So what you would expect here is that this is just the entropy, basically. Like, if there's, that this is just the entropy. That's what this height is. This is the entropy. So that's those are some important things. And you can see matrix, different interpretations that you can get from it. But we're focused again on what we're focused on is this pathway. Okay, so now we have the same, probability weighted matrix, for this example that we've gotten using, expectation, maximization, or just some algorithm that has given us a probability weighted matrix. This is our background, a non-motif, and these are the motif positions. So we have 11 spots in a motif. So one formula is that HK is the height of a full stack at a given position K, is the height of a logo at a given position K again. So you take H max, maximum entropy, minus maximum height minus H of C. And this is just a formula to use pretty much. So I'll just sort of allow you to just see this. This is just a formula that you should use right here. And what you can do is, when it comes to DNA, this is how you find log 2n. N is the number of bases in the alphabet, A, C, G, or T. So there are 4 bases. And then H max will be equal to log 2 of N. So log 2 of 4 will be 2. And another way, in case you don't remember as well logs, and I don't blame you, no, it's been a while in general. So if you have a log X, and then you have think of it this way. This is something that I thought would be helpful. The way you can always remember is sort of like, think of it like a cycle in a way, where what you have is you're going to have your X, So the way it is that you have your x, and your x being raised to the y power will be equal to n. So if you have, so in this situation, what we have is if we have log 2 of 4, what will that equal to? And then we're trying to figure what this is. You know, we're trying to figure out what this thing is over here. We don't know what this is. So we can just say, okay, well, let me just, you know, take this 2 to some unknown thing here. And let me just raise it equal to this right here. So it's just the way that we see it is just going to be equal to 2 to this unknown equals 4. And that's just 2 to the second equals 4. So we have that this part right here equals 2. This part is just the same thing. This part here is just the same thing here. So that's where we get that this H max is 2. So please let me know if you have any questions on that, but that's how you take a logarithm, but you have to just be paying attention to the base. And again, the base here is x. In this example that I was putting here, that's x. That's where we get that from. And then the next thing that we also see here is that we will take this formula log, 2 of 4, which again, which we found is 2 from here. And then we're going to put this in here where we're summing over all the 4 different bases. And if this is RNA, then this T will be replaced with the U. So we have the probability of C of a given base multiplied by log 2 P of C. So again, this is the probability of, a given spot. These are all the K spots here. So this is what this K corresponds to. We're trying to find the height in a particular spot. And then what we will find is we first should find the height. Okay. And when we find the height of each spot, what we want to do is we want to first take these probabilities. So this is, so if let's say we're focused on K being 1, but we will say, okay, well, P of A is going to be 0.116. So that will go here, multiplied by log 2 of 0.116. So that's for A. Then for C, we're going to look at this 0.441, and we're going to plug in 0.441 times log 2 of 0.441. And we're going to get this for C. And then we're going to also add to it, the probability of G in this spot, if we're holding K equals 1. So we're going to get that value multiplied by log 2 of 0.128. And then we're going to lastly look at P, which is 0.314. And then we're going to multiply that probability by log 2 of 0.314. And then look at those values. So CK again is the character in position K of the motif. So here I'm just sort of expanding out what this part is. So if we just see this part here, this part is exactly what this part is over here. So this is how you get these values. And again, this minus. So what I was sort of focusing on in this case is maybe what would be more analogous would just to be seeing this part here. This part is this part, but then, minus becomes positive. So I'm just sort of showing the results. Like if you use this formula here, that's what this will be equal to. And remember, minus and minus is positive, but I was trying to show from, like what is, from the very basic formula from here. And again, please let me know if you have any questions along the way. Okay. So then we just take these values here and just still expanding what these are here. So now, what is this telling us? Okay. Well, we're looking at the first spot. So I just also want to clarify, just in case. So when we have this, so this is again, equal to K equals 1. So that's this first spot. we don't want to worry about, K being 0. So you can just sort of like X this part out. We don't really care right now about the background. You can just cross this part out. We don't want to consider this. We just want to look at these different positions in the motif here, the positions 1 all the way to 11. That's what we want to see. That's what we want to see. And again, that's also shown here where we only looked at spots in the motif, positions 1 to 8. So we don't want to see the background. We just want to get like a sense for the motif. That's what we really, really care about. So we're going to look at the first spot in the motif. So what I'm going to do is I'm just going to zero in what we're looking at. We're just going to crop this part out here, and we're just going to look here at this part right here and just see, okay, K equals 1. And again, we're going to ignore this part right here. We're going to ignore this and just focus on this K equals 1. So what we see here is we're going to use the formula 2 right here, minus this whole formula becomes this 0.116. So this part maps. So this 0.116 here is going to map this part right here is going to be this part right here. And then what you'll see here is that this part right here, 0.441, is going to be this part over here, which again is going to be this part here. And this other part here is going to be this. So, and then you do the same thing for this other part, where you see, okay, G is 0.128. So that comes, from this part here, that's what this is times this. So for each value, you take the probability of that base. So this is the probability that, so again, what this is saying is this one right here, probability that C1 equals A. That's what this is. So all of these sum up to 1. And this is the probability that C1 equals C. So just to keep in mind, for any given spot, the probability that CK equals A plus probability that CK equals C, that CK equals G, should always add up to 1. That's what the probability should always add up to 1. So this is CK equals 1. So just to keep that in mind. So like we just finished like doing this for the other one. So this is this part times this part. And then lastly, we have the 0.314, which is what this is, plus this part over here. And then here you just simplify it out. So you could probably set this up into Excel as well. That, is easier. You could set it up into Excel to then do those parts. And to clarify again, just to make it, just to, bring it home a little bit. So this is C1. Like what all these bases are, these refer to C1 over here. Then this part here is like C2. This part over here, for instance, would be C9. And this part like here would be C11. So that's just, how like the different positions, and these are the probabilities. So this is the probability. This value right here is the probability that C9 equals A is equal to 0.971. So those are the probability values. And then like similarly, what this is going to be is this is saying that the probability here that C9 or C11, sorry, C11 equals A is going to be kind of a lot smaller, which is 4.85. So we kind of say, oh man, this is really high. So we would really probably expect a high information content here, because this value 0.971 is like, it's almost definitely going to be an A in that spot. So that's how you interpret what these are here. And just for more completeness, let me just also say, okay, this value right here is the probability that C4, C is 0.864, And lastly, another example would just say that what this value is saying is that this is the probability that C6 equals T is approximately 0.408. So those are, again, how you interpret these positions. So these are K. And again, just to clarify for this part, we really are not super concerned about this part. So we can just ignore the background positions. Not concerned about those. Yeah. Okay. So that's how we calculate this probability. And then we use this formula here again. So this is the key formula that we use. And we get H1 is equal to this is the height. So, we can just continue working through this example where, we have calculated this height value here. And what this is, if you do this in Excel, what you would find. So this part is going to give you, and another way to see this is that this is how you could set the same formula up in Excel. So you would say this part here is going to be the same thing as HK comma A, which is H1 comma A. So that's this height. So given this formula, I also want to show you another way to write the same formula, which you can use. You can also say that it could be H1. Or in general, yeah, let me use H1 is equal to 2 minus oh, sorry, this should be yeah, the same idea. Maybe let me just make this align closer with this formula. So this would be the G and this would be the T. So the same exact idea. Now, what is this again? This is just the same thing as what this part is this here. This is just saying probability that C1 equals A times log 2 P of C1 equals A. That's how you get this one. And then what this part is, for instance, this is just the same idea, which is just P C1 equals G times log 2 P C1 equals G, which is this here. And then this is here. So same idea. So what you could do with this, the same exact idea is what I'm trying to show here, where this part here is just this part right here is just red, and this part here is what I was trying to capture in green. Like right here. And this green over here. So that's sort of like, and the same thing for 1C and 1T. So you can use the same formula here and just multiply these out for a spot. So what I'm trying to show you is that this part here in red, this is when you calculate it out, you'll get when you calculate what this part is over here, you're going to get 0.3605. When you calculate what this thing is over here, for the G, you're going to then get this value right here is going to be this. So that's what I'm trying to show you. So you just calculate them all. You can do this in Excel or somewhere that does it faster. And in the end, once you find these, you're going to have, you find this total value here, and the entropy is just going to be 2 minus that value. This is the height. So this right here, this part right here, so let me just clear all. So then I just want you to see that this right here, let me use another color. This value right here is the same as this value right here. So once you calculate what this is, so these parts, you just sum them up and you get this value here. And this part, as you remember, this is your HC from the formula. You know, of all the bases, this is a giant C from all the bases. And then this will give you your HK is going to be H max minus your HK is this maximum value minus this value right here. So it's just going to be 2 minus these values. We'll give you these. So in the essence, 2 minus this value right here is going to give you this. So if you take 2 minus point, so here again, 2 minus 0.333 gives you this value right here. So if you, so maybe I'll show you here, like, so this is your HC. So the way that you get this value is you just take 2 minus HC will be equal to 0.326. So you just apply the same formula. And again, this is just the height of each of these bases, along a given position. So that's how you would use it. Again, so please let me know if you have any questions on that part here. So what you'll see is you just have to, calculate what the height is, which is just the probability of a certain base multiplied by log 2 of that. So again, I'll just write the formula out for you guys here, where you just worry about this formula. If this helps you with Excel as well, maybe you can use that. So for a given spot, if we want to find out what is, the formula to use, let me just give myself a little bit more space here. So again, you'll find that this value 0.2142 is exactly, this value maps exactly to this. Okay, so now let me just explain again. This is our H max. That's what this thing is, the 2 that we found, minus this is how you can see this. So this sum, and this will tell you the height at a particular spot. And again, just remember that this is our H max. And when we calculate this whole sum over here, this whole sum is going to be our H of C. Where for each given base, we know that what the formula is, so again, where we know that HKA is just going to be equal to probability that the character at that position in the motif is an A multiplied by the log of that same probability, log base 2 at that position. So that's the formula to use, where with this part right here, this right here, to clarify that this part right here is just this formula over here. So that these are just the formulas that you would need, and that's how we can pretty much, like, that's exactly what I did here. But if you just want, and you'll see that this value right here, this 0.2142 is just this value here. And I got the sum here by just summing across each of these individual components. You know, this value right here maps to this value right here. This value right here maps to this value right here. This value right here maps to this value right here. And this value right here, 0.5247 maps to this value right here. Then you sum them up and you get this value. And that's what this sum value is, that you just sum these values here and you'll get this. So again, what this part is saying is that you just add these up. And when you add them up, you're going to get this. When you add these values up, for instance, you're going to get this. So I'll just, pause for a moment so you can note this down. And the same thing is analogous for this, where instead, if you want this to be a C, what you're just going to do is you're just going to cross. If you want it to be, actually, let's do G, because that's easier. Like, so if you want to do G, then this would be a G. Slash this out to be a G, slash this out to be a G. And you'll notice that this part here and this part here should be the same. But it's just logarithm of that. Okay, great. So now we're just going to continue on and then just see, again, this is how you calculate again, the height at 2. So you just take this part maps here and here. Then you minus 0.001 of here and here. You point this one of this and here. And then you just, you just focus on this set of values for this region here. The set of values will be, all these values are going to be what you calculate here. And then you sum these up. Okay, so that's how those values work. And you can see the same idea is analogous of, in this example above. What you can see is that this 1.607 that we find here, the same as over here. And to remind you that this is our H2 comma A. This is our H2 comma C. You can see this H2A, H2C, H2G, and H2T. That's what this value is here. So kind of going down a bit, now we can just see that we can, continue calculating this. So that's where we get that value from. We can continue calculating this for H3 as well, and we'll get this 0.373. We focus on just these values right here for the third spot in the motif. We focus on these values. Actually, let me just say we focus on, oh gosh. We focus on these values over here. So for H3, we're just going to focus on these values. That's what we get here in the end. And then we sum them up. We sum them up, we get this value here. This value right here. We subtract it from 2. And then we get this value here. This is, we just take this 2 minus what this value is. And then, that's what it gives us. So that's for the third spot in the motif. So we've gotten the height there. We do the same for the fourth spot again, and you'll see that, we ultimately, this also maps to the same idea here. So we could just continue doing this. So, we get this value in the end, which is what this is the fourth spot in the motif. So yeah, we just continue doing that and just using and applying this formula again. And, I'll just say that that's how we get this fourth value. Again, we can do the same for the fifth value again. And the sixth value, we get this value here. This value right here, this 0.738. This 0.738 is going to be this fifth value over here. We're also going to get H6, which is 0.402. 0.402 is going to be here. And then, you could see the same set of values that we're using here. Again, for the 7th, what you're going to see is, let me just bring this down again, just to, show you guys again. This is the 7th, and the 7th one, what we focused on is we just focused on this. In the 7th, we just focus on these values right here. And these are the same values that we are using here, 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 here. So that should be, you should see this part here. Please let me know if you have any questions. And then this is 1.484 you've gotten. And again, this is the probability that, this is the probability that C7 equals A is just going to be equal to 0.068. So that's equal to approximately 6.8%. So that's a probability, like this probability right here, so it's not as clear. And this value over here is just saying that this is the probability with approximately 1%. And that's where you kind of put this part here and here. And then for the orange part, it comes here. So that's how you kind of, work through that example right here, please. And let me know if you have any questions. So then we can see here basically that this is how you calculate these values. So this value right here is ultimately, like, so this 0.51, this value maps again to, this value maps right here to this value right here. And the final value of this maps right here. And then this is the H max of 2. That's what this is again. H max is 2. And it could depend on how many you have using the logarithm. So this is our H max. And then this value is just here. You can compute the heights. What you're going to tend to observe is maybe we have, some differences in the heights based on the probability weighted matrix. So again, we do the same thing for 8 and 9. These are the values that we get here. So I'll just pause for a few seconds if you want to just see again, like, for this part, what we'll see is that this is H of 8. It's focused on this. That's for this part right here. And then for the last one, and this part of this here is this. We're almost there, and also this part here. And then you have H10, which you'll get is 1.759. I'm just showing you again that, what these results are the same. So 1.759 here, that maps here. And then for the last spot in the motif, we get 0.326. And that's what we've gotten over here. So since we're only looking at the sequence logo for the motif, we don't look at the background characters. So that means that we do not look at k equals 0. We only look for k equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. That's what we looked here. So based on the number of bases in our motif. So this is just me taking all the values that we've gotten and just putting them in here. So this is just, the final values that we got, which let me bring this here and just show you guys that this part is just the same thing. I just kind of took these values and I just said, okay, well, this right here is this. Maybe I should do that nicely. This value is this. This value is this. These are the same. Pretty nice, rainbow. color. So these are the height of the entire stack of characters in each position. I'm just kind of mapping them, just, putting it in the clean table. And, you do this for all of these, please. You finish up all of these depending on how many positions in your motif. So again, because our motif is 11, that's why this is 11. So this will just depend on the number of, bases in your motif that you have. So this is just a motif position. And this is, again, because this is our motif has a width. That's why. So then we just determine the height of individual characters in each position. And we get this part here. And yeah, this note for these positions, these are the given, breakdown of values that we have at each position. So let me actually just bring this part down right here. So what we have is this is our probability weighted matrix that we had. So let me just bring this part here and show you guys that, from a probability weighted matrix, I was just focusing on this part. We're going to just cut this part out. Again, we're not going to focus on this. Not going to focus on this part. We're just going to focus on, the motif positions here. So these are just the same things minus the, heading. So it's just same thing over here. Just I put it again twice. So what you're going to observe is, so I don't want to confuse you. So what we're going to say is we're going to take our total height that we got at each spot. So we know that it's this value here. And then we're going to multiply that height by the probability of observing that base in that location. And that's going to give us the height in each spot for A, C, G, T. So why is this different? You might be wondering, okay, well, shouldn't this be the same as this value here? Shouldn't this be the same? No. The idea is that we sum these values up, and maybe it would have been the same if we were like multiplying it by 1.7858. Then if we multiplied this by the probability, maybe it would have been, somewhat. But no. The idea is that what we're looking at is we've already taken this sum and subtracted 2 from it. So it's not exactly the same, but it's all these are all monotonic, so similar transformations. So the higher these values are, we would expect, and in general, these values come from what these values are over here. So what you're going to observe is that in the spot 1, so let me kind of illustrated this way, that these values right here, these are, what these values here map to. Oh, wait, let me just make this. These values are here. So what you're going to find is that in this first spot, we're really likely to have this is our A, C, G, T. We're really likely to have, let's say, a C in this spot here. So that's why this is higher, and these values are higher as well in general. So what I want you guys to take from this idea is the idea that pretty much, I think, when you focus in on this example of 0.21242, you have to multiply it, the height, by the probability of that base. And that will give you, out of this total height that we've gotten of this 0.214, what is the contribution of each of the bases to this? So this is just like a whole, like a overall whole, like a piece, like the overall idea. So you just divide this among the probabilities of each of these. So if you look at this overall height, what is the contribution? Like, this is the height value. And this overall height that we're observing is this. It's going to be this value here of 0.214. 2, 1, 4, 2, 4, 2. And this is the total height. What is the contribution of each of these bases? Again, this is A's height, then you take and you stack on top of that. Maybe you'll take some other height and then some other base. Maybe this is this one, and it's not drawn to scale. Maybe this one contributes a ton. So you just like stack them on top and you'll get this cumulative height. You just stack up the contribution of each of the bases to this total height that we observe. So that's the formula. So you just take this total height, and then for this value here, you just have to multiply this by, this height by the probability of that given base, and then you'll get what this is equal to. So you just take this value here and you multiply it by, take this height, you multiply it by the probability of having an A in the spot, and then you'll get that value. And the probability, and again, the probabilities that we have is, these are the probabilities 0.116. So that's where this comes from, times this height, this height value we got from here. And again, that's what we can also see here, that this, 0.214242. So that's how we get these height values. And we do the same for the second spot. Take the heights and multiply by the probabilities of each of these, respective bases in that spot of the motif. And this K is 2 in this spot right here. That's what this is. K equals 3. So pretty much when we have a total height, and just to bring it home again, is that for your height, you can find base contribution of base. So this is C, but C can be any of the 4 bases in position K. It's just going to be equal to this H of K multiplied by the probability that CK equals C of having that base. So again, C can be, it's in the set of A's, G's, C's, and T's for the DNA, but it's different for RNA. So again, that's a formula that you use there. And this is the height 3. This is the formula you'd use again for here. This height value. This is for the 4th one. Let me also bring down the probability weighted matrix for your reference. This is for the 4th one. But you'll see that we're just going to focus on these values here, and that's what we get here. Right, yeah, that's what you'll observe. You just need the probability weighted matrix, and so you just need, basically, in essence, you just need these 2 things. You can take this, and this is the same, one used to the other. You can just take this matrix, get this table, and just take these 2. And from this table and this table, you'll be able to get each of these contributions. And the same for position 5. These heights are the same as, we plug in here and here, no, here, sorry, and here, and here. You get the heights, and all of these, when you add them up together, all of these, when summed together, will give you this. Position 6 this is what you'll get. So you keep on doing this. Position 7. So I'm going through kind of fast, but I know you could pause this. So please let me know if you have any questions. This is 8, 9, position 10, and position 11. So you're going to end up getting, I know it's kind of a bit messy, so what you'll end up getting are these heights right here. So all you do is you will get these heights in, like these are the heights. HK times these. That's what these will be. These are again, just to bring this home, this table is almost slightly messy in its appearance, but like what I want you to see is that these are, let me just put this right here so this look a little neater. So just to explain again what this is this will just say, this is here, this height in this final position. But this part is here, this is the C. And then this is the T. Oh, oh wait, sorry, this should be the, yeah. And this one right here should be this. So what you will notice is that, as expected, that this is our total height in this position. And that's what this is over here, this total height. This is the total height of each. So we're looking at the height of each base. Again, we're looking at the height of each base in the sequence logo. The sequence logo. And this is position, this is for K is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So these are the heights of these different positions that we're using. So I hope that this kind of makes more sense. And then, this is what you do for position 11. So this is like, position 11, these are the heights that we have. And you're going to expect these will be the heights that you'll expect right here. So for the 10th one, these will be the values you got from there. And let me also just bring down the probability weighted matrix to kind of bring home again why you have certain expectations of what this would be. So what this is telling you is that this value right here, what this is saying right here is that this is 0.458. So we're really likely to see an A in this spot, right? So when we calculate a height over here, we expect that this value is, so it's compared to these values, it's higher than these values. So we expect like a lot of, A in this spot over here. And maybe the rest is kind of split. But in a spot where, like in these two spots, where actually it's a pretty high breakdown of, where we actually have quite a bit of A, or one base in particular, that the information content is going to be a lot higher. So the height typically corresponds to how much information do we have. And as I mentioned, like in the toy example, when we don't have enough information, where it can be 20, 30, 30, 20, like the height's going to be much lower. So in a situation like this, where it can be one base, but it's also the other. So it's still high. Like, so don't get me wrong, it's still pretty good, but it's on the defense. It's not as useful necessarily. So the height is much lower than over here. Here we have a lot of information content. So we know that like it's going to be much closer to 2 in a way. Like, it's going to be that and again, these sum up to 1, but I sort of just rounded it, keep the number. Here, well, we were to compare, okay, well, what's going on here for this base? Oh gosh. So what's happening here, okay, equals 8, And this is also the same as over here. What's happening here versus, if you were to compare this part here, oh gosh, like if we were to compare this part here with these parts with these parts, what we would say is that, well, this seems like it's more of a majority of one base, which corresponds to having a higher height of 0.83994. So the base that's the likeliest will be given the greatest height, because that's how the formula looks. If you look above, you take the height, and in that spot, whichever base is the likeliest will get the greater chunk of the height. It's going to make up more of the height. So you're going to notice that this overall sum is going to be higher when it's likely to be one base, like when we have more knowledge. Like we know that 76.6% of the time in position 8 of the motif, you'll find a base G. So that's quite a bit of information. So this height is like 0.83994. So that's higher than knowing that only 48.5% of the time you observe an A. So that's like 0.15. So this is sort of comparing the majorities. So if we were to compare this value maps to this value over here with what these values are, what we're going to see is that, okay, this is a lot higher, and this corresponds to this being much higher, then this is a lower probability and corresponds to a lower height. So if we compare these two, the greater the probability, which is here, this is a higher one, it has a higher height. And overall, it's going to have a higher height overall, like in total versus this. So this tying in together the observations that we had, that we talked about in the beginning, when we're first exploring how does a sequence logo work, we see that the more information we have on a given base in a particular region, the higher, so if we know this is like 70%, the height is going to be super high. In general, maybe I didn't draw it right, but you can probably see this could be a little bit of a better illustration, that you can see that this height is going to be much better, much higher. See, it's a smaller gap, the same line, perpendicular right angle. So it's going to be much higher because we're going to have more information. Like we know 70% of the time is going to be a C in position 8 of the motif. So that is what we're going after. Frequency logo is just like, okay, well, what chunk does it take place? How much, if we had to divide the pie, how much does each base get? And these all have the same uniform height, but we know the height is just corresponding to the probability. But here, this is corresponding to information content. It's a form of like information contents, computer science concept, like how much information are we getting from this? And it's also related to like mutual information down the line as well. It's all like, branches in computer science of how much information do we get? And the more we know something's probable, the more we have information. Like if I have something that can predict between multiple outcomes, that it's this outcome most of the time, that's still like a lot of information. And sometimes for predictive models in machine learning, even if the baseline accuracy, if we just flip a coin, is 50%, if we can get a model that gives us 60%, it says that it's something like this, it's still like helpful. And actually in this example, like the baselines are 25% for each base. It's equally likely. So if we can know something is even more than that, the more that we know about one base, or maybe a couple of bases, the better. Like if we know that one is like much higher, like 60%, then that kind of gives us more predictive power in a way. And that's why we have more information in, position 5, but here, like in position 8 here, like we really know it's a C, so that gives us even higher information content. So if we definitely know it's like one base or the other, then that gives us more predictive power. So we want to always compare with the baseline and see, can we really come up with conclusive results? So we are given this probability weighted matrix, and based on that, like what I want you to see is that, the more probable some bases, the higher information we'll get. So towards the end, when we calculate it, these are the same values that I was showing before. The information content logo that we ultimately get is going to be kind of what we expect in a way. I know this is kind of long. This is like 11 motif positions here that we have, but we see here that we get much less information. Here for these two A's, these correspond to these values here. So like let me use a color that is, yeah, like so these values here these values right here, will correspond to like this. That's what these correspond to, that height there. And this is like 1 point, these are the great values. We got a lot of information here and here, and these correspond to these, right over here, 1 point. And we can see, is there any other spot where we have that much, like ability to make these predictions? It's like pretty much like you don't even see the other bases because they're so rare, right? And if we map these, this is like this value right here is corresponding to, this 1.76 part corresponds right here. So we can see, okay, well, maybe in, if we were, again, like maybe I should just finish, making this analogous. So these are the K positions. So this is 1, 2, 3, 4, 6. And again, this is, 1, 2. These are all the positions in the motif. So what we're going to see, okay, well, 2 also seems like it has a pretty high, like 1.60, right? And then we can like scroll down a bit to see, okay, well, why is that the case? Okay, well, we have 0.944 over here. It's not quite as high as these values here. It's not quite as high, but it's still pretty high, like 94.4% of the time do we expect a T here. So it's still pretty high, right? But this is like almost definitively you should expect an A and an A in these last 2 spots. So this is still pretty high, but because it's still not almost like 100%, like this is pretty much like really good. It's just not quite yet there because it's like, there's still like a 1% chance of being a C, G, or T. So it's just not quite perfect yet, so it's really particular. But like this one is saying, okay, well, about 6%, 5.5% of the time we observe something else. So there's still this chance of the other one. So you can see they're really tiny. Then this one is not so great. So this is an AGT. So A is like much higher, but then it's also like, there's a G and a T that are quite close here. So this is how we would take this, probability weighted matrix on a more complicated example with the larger motif, and how we would map it to, a sequence logo. So this is sort of like how you go from here to here, which is analogous to what I was saying in the beginning, that we are just trying to go from, we were trying to get this part here. And that's what, I was showing you how we work through that example and how the heights don't always have to be the same and how we can calculate those heights, that when we put it into, a sequence logo generator, we can get this information content logo. And this says that we have a lot of information in these spots here. We don't quite have as much over here. We really don't have much over here. You can see that in the first spot, it's also pretty bad because, it's like, it can be 44% chance for C, and, like P also ties. So I just hope that this makes sense about how we can get the sequence information and say, okay, yeah, we definitely really expect a lot of T's in the second spot and A's and A's. So if you had to make your best shot of what the motif would look like based on this, and if you had to interpret what do you think it looks like, what you could probably, like try to say is that maybe like if you really had to just guess, you could probably just say, okay, this seems like it's a C, this one like a T. Maybe that the best one is usually the one on the top, but like just use the guidance. Maybe let me do it this way, but I just sort of just say a C, a T, a T. So, but so it's kind of like it's more agonizing the smaller the height is. C, you can see like I'm like T, yeah, like this one I don't feel so comfortable, but like it just says go with a T. But you can see like I'm more uncertain, less information I have about it. So that's what it's saying. It's like I have less information about which to go with, like I'm going to take it. It's like more of a gamble. It's not really something known, So like that's what a motif could look like here, in this situation, but it's more of an agonizing decision. This is a possible motif. So, Yeah, we just talked about how we can, find the heights and probable motifs. So again, I'm Sania. So please let me know if you have any questions. If you found this helpful, please like my video as well. And just please ask me any questions that you have. This is a bioinformatics concept, and I think it's super important, so I'm always here for you guys. So please let me know if there's anything I can do to help. Thank you, guys.